structure module is pretty complicated and there's lots of interrelated topics. So what we're going to do now is just go through that topic and also add in intermolecular forces as well. So when we're looking at the type of bonding, the key thing we have to do first of all is look at the periodic table. Now, if we have metals involved, we're going to have metallic bonding. And metallic bonding involves positive ions in a sea of delocalized electrons. There's only one type of structure you can have, and that's going to be a giant metallic structure. So it's quite a simple route for that. Metals, you're going to have metallic bonding, giant metallic structure. And we'll look at the properties of giant metallic structures a little bit later on. Now, the other one, which is relatively straightforward, is ionic bonding. Ionic bonding is where you have a metal bonded with a non-metal. And in that case, you are going to have ions. Again, there's only one type of structure, and that is going to be a giant ionic structure. And there's more information about giant ionic structures in the video there that you can play if you wish to. But you effectively have an ionic bond is electrostatic attraction between oppositely charged ions. Now, non-metals. This is where it gets slightly more complicated. So you just got to keep a really clear head of this one. You've got covalent bonding. Now, covalent bonding is a shared pair of electrons. You can have two types of covalent bonds. You can have single, double, and triple covalent bonds, where that's the number of shared electrons the two atoms have between them. And you can also have dative covalent bonds, where both the shared atoms come from one atom. But the key thing to note is that covalent bonds involve atoms. Now, when we have a type of the structure, there are actually two types of structure. Let's look at giant covalent structures first of all. Giant covalent structures, there are three you need to be aware of: diamond, graphite, and silicon dioxide. Now let's look at diamond, for example. In a giant covalent structure like diamond, we have billions of carbon atoms all bonded together, and they all share, so we have a giant structure. So each carbon is bonded to another 4 carbons in this 3D arrangement. So a giant covalent structure is when the atoms are joined up over a huge number of covalent bonds, and the number of atoms here can be variable. If you have a diamond, if you've got a large diamond, you're going to have more atoms in that structure, whereas if you have a small diamond, not so many. So it completely varies depending on the size of the crystal. So this is a picture of diamond. So you can see how the bonding works. You can see how each carbon bonds to another 4, and so how that arrangement is going through the whole of the structure. And on the left hand side is graphite as well. And you need to be familiar with the properties of those two substances. So now let's look at the other type of structure, and that involves molecules. Now, in molecules, we have a set number of atoms that will join together to form a molecule. So here we're going to form methane. Methane is CH4. So they share electrons to form covalent bonds, and these form molecules. And a molecule is a group of atoms bonded together, and it represents the smallest fundamental unit of that chemical compound. So for example, for methane, that would be CH4. For ethane, that would be C2H6. And here's little methane here with the shared pair of electrons showing the covalent bonds. So molecules form simple molecular structures, and these have weak intermolecular forces between the molecules. So what do we mean by that? Well, let's have a look at what happens during state changes. If I take iodine, for example, as a solid, you can see that iodine has a covalent bond between the two iodine atoms, and liquid is still, that covalent bond is still there between the two iodine atoms, and it's there in the gaseous iodine as well. So what we've broken there is intermolecular forces between the molecules. We haven't actually broken any covalent bonds there. So when we go back and we look at the 3 types of intermolecular forces that you now are aware of, having studied that unit, there are instantaneous dipole-induced dipole forces, also known as London forces, permanent dipole forces, and hydrogen bonding. Now just be careful where it says hydrogen bonding, it's not a chemical bond, it is still an intermolecular force. Now you decide which one is the most important when looking at a compound. So when you do that, you need to think, well, are there any electronegative atoms? If there are no electronegative atoms, if you want to see if there is going to be a difference between the electronegative values. Now, carbon and hydrogen, there's hardly any difference. Powers between carbon and fluorine, there's a big difference. So let's say there aren't. So it's something like methane or ethane, there's not a huge difference. In which case, we're going to be instantaneous dipole-induced dipole forces of attraction. Let's now consider if there are. Now, if there are, we need to use dot and cross diagrams to work out the number of lone pairs and bonding pairs, and therefore we can work out the shape of the molecule. Why is the shape important? Well, we need to decide whether the molecule is polar, or are the bonds, or are the polar bonds in opposite and equal directions. Now, if we have polar bonds, then and we have a polar molecule, for example, water, we then consider, are there any OH, NH, or FH bonds? Yes, yes, there are. So we've got hydrogen bonding involved as our intermolecular force. If there aren't any, then we're going to have permanent dipole forces of attraction between the molecules. So key thing is there, when we look at that, we've got hydrogen bonding and we've got permanent dipole to decide between. If we've got polar bonds but a non-polar molecule, for example carbon dioxide, that's because carbon dioxide is symmetrical, the dipoles will cancel each other out. Then we have instantaneous dipole-induced dipole, so a similar case as if we had no electronegative atoms in our molecule. So three types of intermolecular force. When you come to rate their strength, we know the instantaneous dipole-dipole is the weakest, followed by permanent dipole-dipole, followed by hydrogen bonding, but that's only for molecules of a similar size, a similar number of electrons. So here's a little summary for metals that you need to be aware of: giant covalent structures, simple molecular structures, and also ionic compounds as well. And you need to think about the type of melting and boiling points they will have, whether they conduct electricity or not, and that's all been covered in previous topics.